Capacitors are an electric device relatively few people know about, but that might be considered surprising, particularly when you realize that practically every electronic device will contain capacitors of some kind. A capacitor is a component that stores electrical energy, until it gets full and then releases it in a burst. There are many reasons why you might want to do that. You might store charge in a capacitor in case you lose external power, so that the device doesn't die instantly, allowing the recovery process to complete. You might want a circuit to get a regular pulse of energy every X amount of time. But whatever the reason, capacitors come in all kinds of sizes, holding anything from tiny amounts of energy to huge amounts. Capacitors really are used everywhere, from computers to televisions to high-band pass filters to car starters. Almost every electronic device you use contains capacitors. And the title of this lesson, Capacitance, is a measure of a capacitor's ability to store charge, measured in farads. A capacitor with a larger capacitance will store more charge. The definition of capacitance is given by this equation. Capacitance C, measured in farads, equals charge Q, measured in coulombs, divided by voltage V, measured in volts. So for example, if you connect a 12-volt battery to a capacitor, and that battery charges the capacitor with 4 coulombs of charge, it must have a capacitance of 4 over 12, which is 0.33 farads. If the capacitor had a higher capacitance, it would store more charge when connected to the same battery. Because of this equation, we can see the capacitance is therefore measured in coulombs per volt. So it represents how many coulombs of charge will be stored in a capacitor per volt you put across it. Okay, but what physically makes a particular capacitor actually have a different capacitance? What decides how much charge it stores? Well, that's based on the actual physical characteristics of the capacitor. So we have another equation for capacitance that looks like this. The capacitance of a parallel plate capacitor, a simple capacitor that is just two parallel plates separated by a distance d, is equal to the relative permittivity of the material between the plates, K, multiplied by the permittivity of free space, epsilon 0, which is always equal to 8.854 times 10 to the negative 12, multiplied by the area of the plates, A, measured in meters squared, divided by the distance between the plates, D, measured in meters. Most of that is pretty self-explanatory, but K, the relative permittivity of the so-called dielectric material between the plates, is generally either equal to 1 or larger. If there's nothing between the plates, K equals 1. If it's air between the plates, then K is pretty much still equal to 1. And if it's a different material, it will be a number greater than 1, depending on the exact material. So those are our two basic equations for capacitance. But as usual, now